All right, welcome. So this is Intro to Scientific Computing Languages. Today it's crowded, but I promise in 2 or 3 lectures, half of the people will be scared away. So there is gonna be room for everybody. So this semester we got popular, and we will be taped. Please don't be shy. I really want the class to be interactive. I see familiar faces, so some of you already know my style of teaching. I really want you to ask questions. I really want you to say stupid things because you don't know what's going on. So inevitably you will say stupid things, but that's okay. Everything will be in English. If you don't understand my English, you can please ask to slow down, to repeat. Don't be afraid of anything. I speak English, and other languages I speak are also C, some Fortran, some Lisp, and so on. So if you don't know how to express yourself in English, you can use some of the other languages. Everything is fine. All right, let's start. Today, normally, my first lecture is only a short intro, but since I will be skipping a class next week, today we have a regular class. This is just 7 short slides on what the class is about, how the exam is, and what you guys are supposed to be doing during the semester. And then we start with a proper class. So lecture times today, Tuesdays and Thursdays, from 5 to 6:30. It's always here. And all right. I showed this one slide. Actually, somebody else showed it for me. I was not in Germany at the last Friday, so maybe some of you have seen this already. I just want to say, what are the objectives of the class? I want to show this dichotomy. Dichotomy means contrast between fast and easy prototyping, so languages for make your life easy. So you get to prototype, to put down some program in a quick and easy way, versus languages that let you attain high performance. These are not nice and easy languages, but they let you squeeze all the power out of the computer. So Matlab and Mathematica, that's what we do for the first category, and C for the most part. We will not do much Fortran for the second category. Okay, what are the topics? A little bit of a syllabus. We will see the difference between computations that involve numerical numbers and computations that involve symbols. So numerical versus symbolic computations. I think on Thursday we will already look at floating point arithmetic. Normally I give this lecture later on in the semester, but I figured I have to cut you guys down to maybe half of the size. So let's do something boring right away, and you will drop for sure like flies. Conditioning of a problem follows. It's another boring topic. At this point, the boring stuff is over, and we start looking at actual languages. So we will look at Matlab first, and Matlab follows an imperative programming style. After Matlab, we will look at Mathematica, and Mathematica follows a functional programming style. So we will look at other contrasts. And then the final part of the course will be on high performance. So we leave Matlab and Mathematica in the back, and we look at C. Okay. This is the outline. So today is number 1, and probably Thursday is going to be number 2. As I said, then it's going to be Matlab, then it's going to be Mathematica. Now, how to access Matlab and Mathematica? Every student of RWTH has access to the Rechenzentrum. So, and from the Rechenzentrum, you can access Matlab. So that's easy. Everybody can do that. For Mathematica, is a little bit trickier. But I bought, through my institute, I bought some licenses for you guys. I think I have about 20 licenses. So depending on how many of you will stick around, I will give either individual licenses or maybe in teams of 2. We will see how that works. But so you don't have to worry about purchasing anything. After that, I think I will do 1 or 2 lectures on visualization. And then, as I said, we switch to performance. All right. Now, this is, I think, the hot topic for you guys. I want this to be clear since the beginning so that nobody gets confused. What is the exam like? The exam is an oral exam. But we start with 5 assignments throughout the semester, which is not a semester, but it's okay. These 5 assignments, some of them will be individual, some of them will be team assignments. You are supposed to solve the assignments, then you turn them in by email, and I will look at them, but I will not grade them, so you will not grade right away. It's just that I want to see how you guys performed. If you guys perform really well, I think at the end, if you perform really well in all of the assignments, I think at the end, let's say that you have a grade of X, you will get a grade of X plus 0.3. So if you had 1.7 in the end and you have done a good job in the homeworks, you bump up automatically to 1.3. There are going to be some challenges. 2 of these challenges will involve speed, not speed of programming, but speed of the program. So how fast your program, your C program can go, how fast your Mathematica program can go. Also, we care a lot about elegance. In prototyping, the important thing is that the program is not fast, but it's clear. It sends you a message. It's almost like a piece of art. So we will have 3 challenges, I think, and the winners again will get the bonus for at the final exam. Especially the challenge in C, it's pretty cruel. The guys spit blood against one another. It's pretty intense. It's fun. Okay, so those are ways to increase the score. Then there is the final exam. It's by appointment. So we decide. You guys show up in my office and you will present a final project. What is a final project? I think I will make it a little bit easier with respect to what I had the last years. So it's going to be most likely a project on a form of poker. If you guys are into poker, you have an advantage. No, I'm kidding. It's going to be a simulation on a poker simulation. Most likely, you should be able to solve it in different ways, either analytically, so with let's say Mathematica from a symbolic perspective, or numerically, so running simulations. That's up to you, and I also leave the choice of a language to you guys. Unfortunately, you only have 3 choices, which are Matlab, Mathematica, or C. Last year, the guys were lucky. They also had Python, but nobody used Python. So, depending on time, we might do scripting, shell scripting, possibly, yeah, TC shell, bash, but I'm not sure. It depends on how far we get into the semester. All right, this is advertisement. On Thursdays, for those of you that are interested in some different languages, maybe new languages, exotic languages, I am organizing this seminar. It's at 4 p.m. So in 2 days from now, if you're interested in this, please show up. I have to see how many people are interested, and then I will pick some topics. I will give you a couple of papers for you to read. And basically, the whole seminar is about learning these new, not so well-known languages, possibly from a scientific computing perspective. So is Python good for scientific computing? Are Lua or Scala good? What are the problems for scientific computing? So if you guys are interested, you show up, then I choose some topics. And I will start off with a talk where I teach you how to give talks. And then we take a break, maybe, I don't know, 1 or 2 weeks. And then you guys start presenting. Okay. I see some familiar faces. Some of you have taken my next course already, which is high performance matrix computation. Actually, I think next semester I will be teaching automatic generation of algorithms. I have to decide. All right. Course guidelines. This is super important. These are the things I really care for. Let me explain how it is. So on the left-hand side, there is me, and on the right-hand side, there is you. This could be a long process, but I made a long story short. So I teach, you listen. This is easy. Maybe you don't understand, so you ask questions. That's perfectly fine. Then I repeat and clarify. Then I ask questions, and you guys answer. This is important. Then I assign homeworks, and you do solve the homeworks. And this is the most important part. You guys don't sleep. It really pisses me off if you guys fall asleep. You can eat, you can read, you can drink, you can do whatever. Just do not sleep in class. Okay. For the exercise sessions, things are a little bit different. Normally you teach, and I listen. Then I ask questions, and you guys clarify and motivate, and none of us is sleeping. Okay, questions about this? You are supposed to have some questions, at least about the exam. Everybody has always questions about the exam.
So about the seminars about languages, will it?
Yes.
Will it be during the whole semester or some weeks? That's all?
Yes, it will be during most of the semester. So we meet this Thursday to decide actually how many of you guys are interested, and then when to meet next. I want, as I said, I want to have a lecture right at the start to tell you how to organize a presentation, how to give a lecture, and then we will meet probably a little bit later on in the semester. Other questions? Yes?
When the final project will be defined?
The final project will be defined or assigned? Defined. It will be assigned at the very end of the semester, maybe 1 or 2 weeks before the semester ends. So if you guys want to start early, you can, but yeah, not so soon, not in the middle of the semester. You had a question? Yes.
Clarify again why you turn on Python in comparison to last time?
Because that's an interesting question. Thank you. So, because I found that while Mathematica and Matlab have a clear place, they cover different places, different parts of territory, and C covers the whole other side. Python was a sort of overlapping, can do a little bit of everything, but doesn't do any of what Matlab, Mathematica, or C does as well as them. So in the end, I found that it was sort of a taking out time from the other languages, especially when we get to functional programming. Most of you will struggle, so I prefer to spend an extra lecture there, and I prefer to explain things more thoroughly than to, do something that you can anyway do in Matlab, Mathematica, or C. Other questions? Yes?
So Tuesday will be the lecture, and then Thursday will be the exercise?
Thank you. I forgot about that. Yes, that's absolutely right. I don't know how you knew that, but that's right. On Tuesday, I will always lecture, and on Thursday, I will lecture and discuss the exercises. Normally, I will assign the homeworks on Tuesdays, and we will discuss them on Thursday of the week after that, so that you guys have 9 full days. I forgot that. Thank you. Questions? Can we start? All right. Lecture number 1. Okay. What do you think a programming language is? Yes.
A formal representation of some kind of algorithm.
That's interesting. Yeah, I would agree with you. What is the purpose of a programming language? Yes.
A way to communicate with a computer.
Didn't you take my class last year?
Basically,
Cheater. Yes, he knows the answer. That's a way to communicate instructions to a computing device. I'm happy. It means that last year you learned something. So you still remember a year later. That's good. So it's a way of instructing a computer. Well, actually, I say a computing device. So we will have to see what a computing device is. These instructions and constructs are put together, are organized together, and they form programs. Okay. Here is a short list of languages. There are more languages than you can imagine or that you can think of. These are just probably the most popular ones. I will show you some history of languages in a few slides. Now, let's go back to computing device. Do you remember what a computing device is? No? Damn. What is a computing device? Any? Sorry? CPU is a particular computing device. Nah, it's part of a computing device. Some other take? Yes?
Device that executes instructions.
So it's almost a catch-22. Yes?
Turing machine?
Oh, you're going computer science. Okay. Turing machine. We will talk about Turing machine very, very briefly. Let me tell you what a computing device is. It's a processor, basically. It's anything that computes. But you don't have to think about a computer necessarily. Cell phones are computing devices. Or, you know, if you enter the cabin of an airplane, there is plenty of computing devices. You can think of anything that goes from a sequential computers, processors, to embedded processors, what is in our cell phones, what is in even watches and stuff, all the way up to the largest computing devices, which are the supercomputers. All right. Here is a picture from early 2000. It's a crappy picture, but at least it tells you what is inside the processor. Here I spell out some of these components. For instance, where is the ALU? Here you go. ALU, that's the arithmetic logic unit. That's where the actual computations happen. When you multiply, when you add the numbers together, those numbers are actually here. They are multiplied here, and they are spat out somewhere else. Then we have, well, floating point unit, that's the same, but if you have a floating point numbers. Prefetching unit is something that goes into memory and fetches data or instructions. Registers is where the data actually is, where the numbers are. Okay, how to tell these components what to do? That's exactly what a language is supposed to do. A language, some languages, actually for the most part only one language, tells the processor where to go get the data, where to move the data, what to do with this data, and so on. Which language is that? Anybody knows? Yes.
It's not assembly.
It is assembly.
So assembly is usually binary code the CPU executes.
Okay, so the assembly is the language that allows you to do all these movements. What you're trying to say is that the assembly is not directly executable, and this is correct. The assembly is converted, transformed into binary, and the binary is the actual code that guides the processor. Unfortunately, you cannot program in binary. You program in assembly or something above assembly, and that is translated into binary code. So assembly is pretty much the only language that allows you to literally control these units. Every other language is a high-level language compared to assembly. And at that point, you talk about what you want to do. So you want to multiply two vectors or a matrix and a vector. You want to do a fast Fourier transform or whatever. And there are languages that allow you to specify that. But for sure, in C or in Java or whatever, you don't say, take this instruction, move it into this register, take these numbers, put them in the register, multiply them together. All of that is done automatically by either a compiler or an interpreter. And I will explain what compilers and interpreters are in a minute. Okay, assembly. First of all, it's a very, very fast language. What does it mean fast? It means that if you write a program in a smart way, assembly allows you to use all the resources of your processor. That's pretty much what fast means, at least for the moment. As we said already, it's not the lowest possible level. So there is the binary, which is even lower. Machine code, in fact. So we need an assembler that takes the assembly, so the program in assembly, assembles it, and spits out the executable. All right. Assembly as the language still has some labels that help us identify what you want to do. By contrast, the machine code is only numbers, so there is no way you can program in machine code. But the important thing is that the assembly is so low level that almost every instruction translates directly to an operation on the processor. In a high-level language, like some languages that you know, it's absolutely not like that. One single instruction of a high-level language corresponds to many, many moves at the machine code level. The assembler, since it's so close to the architecture, is hardware specific. What does it mean? It means that every processor has a different assembly. If you learn how to program one processor and then you move to another one, you have to learn a different assembly. Why is that? Oh, this is, assembly and assembler, both of them. Why is that? Because two different processors probably have different architectures, have different registers, have different components. And the assembly is a language that lets you control these components. All right. We are not going to look at assembly at all, except for the next slide. And then we forget about assembler and assembly. This is assembly. This is a program. Now the challenge for you guys is, what is this program doing? Let me tell you a little bit of assembly, since we're not going to spend more than 5 minutes on this. These are the, as I said, mnemonic labels that help us identify what we want the program to do. These are the arguments of the functions of these labels. So for instance, the first one, li.s, li means load, s means floating point number. That means take this number 0 and please store it into whatever that is, that's a register. Then we have some instructions like mul.s, which is multiply, and .s means, oh look, these are floating point numbers. As opposed to the next one, which is mul, which is multiply integers. Same, add u is different from add s. And add I, actually I don't know what add I is, but that's okay. And then we have if statements, we have jumps, and so on. So anybody, I even left all the comments here, so for sure you know what the program is doing, right? Any wild guess? Not even, as I said, it's okay to say something stupid. All right, I'll give it away. It's computing a polynomial. But it's not computing a polynomial the easy way. It's actually using Horner's algorithm, which is more efficient. There was no chance anybody could guess that. Okay, enough for assembly. Yes?
The variable which is in the comments called I, where does it come from? I never see it initialized or anything. So shouldn't it be just a random computation that you're effectively doing, starting somewhere in the polynomial?
Very possibly. I have no clue. You might be right. And with that, okay, let's move on. Now, what is the oldest programming language that is still used? Very good. Fortran was born in 57, and then it has been updated several times. Actually, Fortran 77 has been very, very resilient. I would not be surprised if you go to your institute and the code from the engineers and physicists, probably a good portion of it is still written in Fortran 77. It took a lot of effort to switch to Fortran 95. What is the second oldest? Almost everybody knows about Fortran. What? Who knows about the second oldest? Yeah? That's, I wouldn't say that is still in use. It's probably the second oldest. No, see, it's much more recent. Yeah? COBOL. Did you say Scala? No? No. No chance. I'm not sure about COBOL. We will look in a minute. It's Lisp anyway. So, oh, here you go. COBOL is in the 60s. So, somebody remembers about Algol, good memory again. And surprisingly, we look at pretty old languages in this course. C is from the 70s, Matlab is from the 70s. Looks like we look at old stuff, but this is the bread and butter of scientific computing. Okay. I expect a good portion of this audience to know the answer. Yeah? No. Okay. Yes? Nope. All right. How many of you are Germans? Come on, guys. Shame on you. The oldest programming language is actually a German language. It's Plankalkül from the 40s, Second World War. It never was published because it was used, of course, during the war. And Konrad Zuse was the inventor for the Z1 computer. Just as a curiosity, the first compiler for Plankalkül was written in 1998. Just, yes?
So that's actually a higher level language.
No, there are computations performed. There were computers for which the language was written. Okay, history of programming languages. How do I kill this? Yeah. Oh no, like this. So this is pretty useless, but it's just for fun. I will put this up on my web page in case you are curious. You see that Fortran is the oldest one. From Fortran starts a line, and you go down to Algol, which is also very old, and COBOL. But then these guys actually terminate. No, COBOL not, sorry. Algol terminates. Sorry. Algol doesn't make it to the end. The really important one from Algol, we go up here, CPL, blah, 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 BC, and this survives all the way to nowadays. And if you're curious, unfortunately, this is kind of old. It goes up to 2004. If you ever find a newer version, please let me know so I update my class material. Okay, back. There is a chair empty there, and probably there is a chair empty down there. So you guys don't have to die. There is a chair empty there. Okay, compilers versus interpreters, or compiled versus interpreted languages. Let me repeat, this is just an introductory lecture. Most likely it's super boring for several of you, but we have to go through this. What is a compiled language? It means that you write a program, and the program is translated into an executable file. It's important to see that this executable file contains architecture-dependent instructions. This means that if you compile on a processor and then you compile on a different processor, you get two different executable files. This is important. Once you have the executable file, you can execute it without even looking at the original program. You don't need the source anymore. You can just use this executable. You can keep this executable and repeat it, reuse it years later, or you can even reuse it to compatible architectures, to compatible computers. So the executable basically becomes your program. What about the program? Is the program portable? So again, the executable is portable to compatible architectures. What about the program? Yes?
Of course, when there's a compiler written for the other system.
Perfect, exactly. The program is perfectly portable as long as you have a compiler for this computer that you're moving to. If you don't have a compiler, it means, oops, I cannot use this processor. Okay, normally compiled languages have the feature of speed. Keep in mind, you start with a program, and then you pass this, your program, you pass it to a compiler. It crunches this program for some time. It thinks about it. It ponders how to optimize it. And then it spits out an executable. So the compiler does the job for you. It tries to really create something that performs well. And normally compilers are very good. At least C and Fortran compilers are historically very good. They really look at lots of optimizations, lots of opportunities to speed up the computation. So compiled languages, normally you can think of fast languages. Examples, C and Fortran. Now let's go on the other end of the spectrum. We have interpreted languages. You start with a program, and there is an interpreter that goes through the instructions of this program and tries to execute them one by one after another. So the compiler had the possibility of looking at your full program and trying to do optimizations. The interpreter looks at one instruction after another. So for sure the interpreter cannot optimize your program as much as a compiler can. The interpreter doesn't generate code. This is not true, but it's a lie, but allow me. And you always need the interpreter. If in a year from now you have your program and you want to execute it again, well, you need the interpreter, because the program by itself doesn't do anything. When you think about interpreted languages, think about ease. It's very easy to try things out. You just write a program, you let it run, and you see if it crashes, if you see what it spits out. It's very easy. You don't have to actually compile and then execute the compiled file, the executable. You just run it. You see what you wrote. You see whether what you wrote makes sense or not. Unfortunately, ease normally comes with the opposite of speed, so normally interpreted languages are slow. In our world, when we think about interpreted languages, we think about Matlab, Mathematica, and Python. Of course, for those of you that know already about languages, I created something maybe too dramatic. There are many languages which are in the middle. So many interpreted languages actually are half interpreted and half compiled. But the truth of the matter is that purely compiled languages, those are the fast ones. And guys from this area are nice to use, are practical, but never as fast as a C or Fortran. Okay, computer programs. This is the one slide about computer science. No, not yet. Okay. This is a little bit of semantics. What this syntax means is that I can describe my computer. By my computer, I mean all the variables or whatever is sitting in memory, whatever is stored in the hard disk, with a description of an initial state. Then we have a program. We execute this program in this initial state, and this program will modify the state. So we'll change the memory. We'll maybe write to disk. We'll maybe print something on the monitor, so it will change the state of the computer. So we'll generate a final state. Okay. What does the program do? It's a function. It takes the initial state and it modifies it. It spits out a final state. So it's an actual mathematical function. It takes whatever it's in the hard disk, whatever it's in your variables, whatever it's on the screen, and okay, it takes your program, it executes it, and spits out a final state. So it's a mathematical function. The syntax double brackets means semantics. Semantics means meaning. So the semantics of P means the meaning of a program. I don't want to explain what we mean by that, but of course, when we write a program, we want it to do something. So in our mind, this program is computing, or we would like it to implement a certain function. Okay? So we would like the semantics of that program to be the function that we have in mind. Most of the times, this function is something that has some mathematical meaning. We want the square root of a number. Okay, my function here is a square root. Or maybe my function is a simulation of a finite element method model applied to a bridge. Okay, we take the input data, we take the model, whatever, and we run a simulation, and it spits out whatever, the stress or whatever we want, the plot. Our program, any way you look at it, it's a mathematical function. And we would like our program to be as close as the real, as close to the actual mathematical function as possible. So how do we decide if our program actually does the job? So how do we decide if it is really implementing the function that we have in mind? There are theories there is a big area of computer science that talks about this. We will not cover this at all, but this is when I want to show you something. Chalk. Okay, so we have our input world. This is where the input data is. And, well, we don't know what the output is, but it's going to be somewhere around here. And I know that if I start from an input data here, the function that I have in mind goes right here. This is the function, okay? But we do not have a function. We only have a program. So, in fact, we will have something that goes like this, and we would very much like this program to take us exactly to the same spot. That's what we would like a program to do. We have a mathematical function in mind, and we would like the program to take us to the same destination. Now, if our program can do this for all the i's, so it doesn't matter what the input is, my program always takes me exactly where the function takes me, then for sure the program is correct. Can you guys comment about this? Is this a satisfactory definition? Yeah?
That would be very awesome, but usually our mathematical functions, they go over something like reals or so,
Mm-hmm.
and there's an unbounded number of reals, so
Okay,
many
that's a good point.
we can never find a program.
That's a good point. So he's saying that what happens if our function over here we get to the reals, and there are a lot of reals. In fact, I will show you that the real numbers are not even representable on a computer. So it's kind of difficult to do this game of checking whether the function and the program goes to the same spot. So yeah, it's a good point. Let's say that we only work with integers. So we solved that problem. We only work with integers, okay? Are you satisfied with that definition of correctness? Yeah?
What happens if we put something in P that it does not come out of I? Something that is
Okay. So you're going for the nasty cases already. Let's say that we are smart enough and we only allow I to be inside a capital I. So we don't take care of exceptions. But of course, that's another issue as well. You're right. Let's restrict ourselves to easy cases. Yes?
Maybe we have the problem that we find an I where f from I is, I don't know the English word, Polstelle, not defined. Something like 1
Over infinity, 1 over 0.
yes. And so for our program, maybe our program won't terminate for this number.
Yeah, okay. But is your function defined in that case?
No.
See, then it's okay. If you wait an infinite amount of time, but your function is not defined, you're happy, that's fine. Let's take infinity out of the picture, because that complicates things. Let's make our life simple. We have only integers, we have finite computations, we don't divide by 0. Is still this acceptable? Let's just say my function, what I have in mind, is the sorting function. Takes an array and sorts it. Okay, that's easy. And it's only integer numbers, okay? So there are no complications. Now I write a program, and I want to see if my program actually sorts it, sorts the vectors. So what I have to do, I only have to go through all the possible vectors and see if my program sorts them. What's the problem? How do I go through all the possible vectors? This is a purely computer scientist type of definition. It has no practical value. It's not that you will ever be able to go and check all the possible vectors. You could do some exhaustive testing if your input set were very, very small, but otherwise this is purely theoretical. Okay, what you will see, probably on Thursday already, is that we do not work with integers, as somebody already suggested, you pointed it out. We work with floating point numbers, so we work with the pi, we work with 10 divided by 3 and stuff like that. And for these kind of algorithms, you will see that even if we have this property, that mathematical property, still we might be in trouble and we might get a completely wrong answer. So when we work with, in scientific computing, we do this all the time. When we work with numbers, formal correctness, this is the definition of a formal correctness. So computer science correctness of a program does not imply that we have a correct answer. And I will show you this. Time, very good. Okay, yeah. Is that a question? No. Subroutines. So as part of our programs, we should organize our programs in terms of subroutines. Here are a bunch of synonyms for subroutines. What is a subroutine? Is a number of instructions that just do one specific task. And these instructions, normally you can move them from one side of the code to another, one part of the program to another, and they will still compute something specific. The area of a circle, for instance. Okay, they look a lot like a mathematical function. We have a name of a function. This can be a subroutine, this can be a subprogram, procedure, however you want to call it. You pass some arguments to them, and that spits out one or more pieces of data. There is a big, big difference between mathematical functions and procedures or computer functions or subroutines. Computer functions might have side effects, and side effects are nasty. Side effects are dangerous. What does it mean, side effect? Let's say that we have our state. I told you what a state is already. It's our hard disk, it's our screen, it's our memory. Then I ask my function to compute the area of a circle. And it tells me the area of this circle is 5. Okay, that's fine. But while doing this, it decides to write something on a file. In a way, it changes the state besides spitting out the result. So it tells me what the result is, but as part of it, it does something else which has nothing to do with the computation of a circle. That is a side effect. And when you program, you really need to be aware of side effects, because these things modify your state and your functions depend on the state. So it's very important to keep track of side effects. Subroutines. Subroutines are good for a number of reasons. First of all, you don't have to copy, you don't have to put your code over and over. If you want to compute 10 circles, you write a routine that computes the area of a circle, and then you just invoke it in 10 different places. You don't put the code for computing the area in 10 places. So the code is shorter and is more meaningful. They enable modularity. You can build a program in terms of modules, of subroutines. Each one does something specific, so this is good. Also, you can take somebody else's module for computing the area of a circle. You don't have to reinvent it every time. They define very specific tasks, so they limit the scope of a piece of code, and so you can try to optimize this piece of code as much as possible. You know that this piece of code will have to compute the area of a circle. You don't have to worry about, oh, maybe I will receive a complex number. Maybe somebody will ask me to sort an array. No, you know that you will have to compute the area of a circle, so you will optimize your code for that. The structure is, depending on the language, the structure varies. Routine name always needs to be there. The arguments, they might be there or not. You can create functions that take no arguments. In fact, you can create functions that have no body. You can create functions that return no value, so pretty much everything is optional except for the name. All right. So now some questions for you guys. We have two routines, or two functions, or two subprograms, whatever. Inside routine 1, I have body 1, so I do some computation. Can I have a call to routine 1 itself? Yes or no? Anybody for a no? I like controversies.
It really depends not only on your language, but also if you want your program to terminate. Because as we see right now, just this abstract representation, there everything is fine. But to implement that, you need to somehow keep track in which version of routine name 1 you are. And some languages simply don't allow that.
I know what you're saying, and I agree with you, but the question is simpler. Is just a can. So, is it possible to? And most of you guys seem to believe that yes, you can. Just anybody who thinks it's not possible? Apparently, everybody is familiar with recursion, but apparently nobody is familiar with Fortran 77. So, yes. But no, Fortran 77, you cannot have recursion. In which case, your only resort is to use iterative programs. What you were mentioning is exactly here. What about recursion limit? What about termination? So, recursion limit means how many times can I go on calling back myself? So I define myself function, and as part of that I call myself, so do the same thing, do the same thing, do the same thing, nested. How many times can I do that? Some languages have a variable, a global variable, or some environment variable, and they say you can only do that 256 times. After that, your program crashes. Other languages, much smarter than that, they allow that to happen only if you are able to provide proof of termination. These are super sophisticated languages, but they're very cool. Okay, as I said, if that is not allowed, it means that there is no recursion in your language. And Fortran 77 is the example. Fortran 95 allows recursion. Question number 2. What if routine number 1, we enter, we get into body, and then from body I have a code to routine number 2. Perfectly fine. But in routine number 2, I have a return call back to routine number 1. So is that allowed?
Again, it depends on the language.
Ah, again, what do you mean again? Before nobody said no. Any other answer? Yeah?
Maybe if we begin with routine name 1
Mhm.
and start a function call of routine name 2
Mhm.
and we call to routine name 1.
Mhm.
The routine name 1 ends correctly, but the routine name 2 not.
No, why?
Yeah, because the routine name 2 had not the chance to finish.
Finish. I see. Somebody wanted to say something, yeah?
But if you try this in C, then you need to define one of the routines before you write the code.
Mm-hmm.
Otherwise, you can't execute it.
That's correct, yes. You wanted to say something?
I think it works fine if you just provide any statement around the Matlab, just
Mhm.
saying that it should terminate if this happens.
So actually routine number 2 will terminate as long as routine number 1 terminates. And this is called mutual recursion. It's by no means different than recursion. It's exactly the same thing. In fact, you can always transform one into the other. Fortran, nope, you cannot do that because that would be recursion. So Fortran 77, I should say. Now the question comes, this is again a computer science. It has no relevance for the rest of the course, but since it's a first class, why not? Are recursive languages, or better, languages that, let's not say languages, recursive programs more expressive than iterative programs? Or can you do with iteration more or less than you can do with iteration? Yeah?
No,
Recursion, sorry. Yeah.
no, you can transform a recursive program into an iterative program simply by managing all the state that's created by a function call yourself and the function itself.
The first part of the statement is correct. The second, I'm not sure. But yes, you're right. You wanted to add something?
I'm not sure about it, but I've learned something about, for example, the Ackermann function.
Mm-hmm.
This is not a primitive recursive function, and I don't know if it's possible for that function.
To be transformed into iterative. Mm-hmm.
Theoretically, any recursive function is transferable to an iterative.
Yes, very good. And here is when we go back to Turing. Both recursion and iteration are equally expressive because you can transform them into, you can execute either of them with a Turing machine. I don't want to go in this. There is a theorem that tells you that anything you can do recursively, you can do iteratively, and vice versa. And if you're interested, I can point you to some theoretical computer science, but it's not important for us. So the result is recursion, yes, is equivalent to iteration. Sorry.
Why did they forbid recursion in Fortran? Because it
Ah.
has no advantage, because iterative programs do not terminate either.
That's a really, really good question. Do you guys want to answer? I see that you're jumping at it. Okay.
Iteration is more efficient in the compiler side than the recursion, and it's more efficient in memory and speed.
It is true. Iteration is normally more efficient. That's not, I don't think it's the main reason. What do you want to add?
If you don't do recursion, you don't have to actually implement function calls themselves. You
That's-
can just take the text from the function
Yes.
and plug it in there. So you save essentially function
Mhm.
calls and just take them.
Yes, that's also true. There is all these problem with the stack. Every time you enter a function, you have to define an environment. You have to open a scope, and I will cover this. There are a lot of operations that come with recursion, and you don't have to take care of them if you only allow iteration. But the real reason for Fortran, I think, is that if you only do iteration, you can do pretty accurate static analysis of your algorithms. You know how much memory you will need. With recursion, you don't, because you don't know how many stacks, how many nested calls you will have. And one of the big concerns of the Fortran developers was to allow the users to specify the amount of memory which is available. This is why probably you guys cannot even imagine this, but in Fortran you cannot allocate a vector or a map or a matrix. You cannot say, okay, I need a 4x4 matrix, please allocate it for me. There is not dynamic allocation of memory. Why? Because Fortran was born when memory was extremely scarce. So the programmer, the user, would say, okay, I only have 16 kilobytes. Please do your best to stay within 16 kilobytes. And things like recursion would easily get out of hand. So that's why there is no recursion. You wanted to say something?
Well, I wanted to add, but if you have recursion in the language, then you have sometimes problems that you can express them much better.
Sure.
And there are optimizations that can, automatic optimizations that can make out of the recursion in the background, the compiler can change them again. So it's iteration again.
As a matter of fact, when we look at Mathematica, we will look at recursion a lot. When we look at at Matlab, we look at iterations a lot. Okay. From subroutines to libraries. A subroutine solves a specific problem. Subroutine, procedure, function. It computes a specific operation. And as I said, it's reusable. You can take it and use it in different parts of the code. If you have a collection of subroutines and all of them do something similar, okay, then you have a library. For instance, if you want to sort and you have different functions to do sorting, quick sort, merge sort, bubble sort, and so on, you can put all these routines together and they form a library. A library is not a program. You don't execute a library. A library is a collection of functionalities. For us, the most common libraries will be BLAS, basic, linear algebra, subroutines. You will hear about this a lot, so I don't have to spend too much time now. These are very popular linear algebra libraries. These two are finally dead, but LAPACK is right now is still the standard library in numerical linear algebra. PATSI is an extension to LAPACK to sparse and iterative solvers. MPI, message passing interface, it's a library to allow computers to communicate with one another. pthreads, same story. It's a library to allow multiple threads to coexist in one computer. And here is a question for you. Libraries can be written in all sorts of languages. Can a program in language X call a library written in language Y? Yes?
Yes, for example, if you have a dynamic link library programmed in C, and you can use the DLL in, for example, your Java program.
Again, what you said is true. From Java you can call C. You used the bad word. You used the word This comes from Windows, so please don't ever say these words in front of me. Okay. That's probably to be censored, but that's okay. What else did you want to say?
Again, it depends. For example, the standard template library of C++ is a library that's distributed in source form and must be distributed in source form because otherwise you can't instantiate the templates. And of course, you can't use it from a language that doesn't understand C++.
Yes, so the right answer is in general, no. It depends very much on the source and the source language and the destination, the target language. Yeah?
You just need to know the calling mechanisms, and then you can just write your own.
You are adventurous. Well, I wouldn't say it's just matter, but let's drop this. You cannot call any language, any library from any language. Let's just say this. Okay, side effects. I mentioned side effects already, but I want to go fast so that side effects is when we invoke a routine in a certain state, okay, and we end up in a state prime that is different from state. Notice that I singled out, I took the variable res out of state, which means res is a variable and I monitor, I keep my eyes on it. And of course, after I call routine, res has been modified. Okay, that's fine. That's what I'm interested in. That's what any mathematical function would do. So res is perfectly fine there. But now state, I have a state and a state prime. And if a state prime is different from state, something bad happened, some side effect. Your routine, while it was computing res, decided to do something that was not necessarily predicted. So, unfortunately, most languages let you use side effects. Print statements normally are considered the side effects. These iterative constructs, maybe you change the iterators, or they do something with the stack that you are not totally aware of. So most languages have side effects. You cannot avoid them, but you should be aware of them. At that point, it will be very important to understand what the scope of a variable is, and when and how a variable is declared and defined. So that's why now we get into scope and we finish our lecture for today. Okay, just one last distinction, imperative versus functional languages. Imperative languages, that's what I think all of you guys are familiar with. You have variables, you have a state, what I showed you before. And then a program is nothing else than a sequence of steps. You do this, okay, then you do that, okay. If this, then do that, or maybe this one, and you keep doing you keep going like this. You have assignments. You have variables that contain temporary results, final results, and so on. The commands modify the state. Of course, you change that variable, you write to a disk, that's perfectly fine. And side effects, plenty of side effects. These are languages, imperative languages. Now, let's go on the other side of the fence, functional languages. So, we start off, we don't have variables. So, you don't store, you don't compute something and store it. You do not assign. Of course, I'm being a little bit extreme. Again, as before, there are objects in the middle, but for now. So you don't have assignments, instead you have mathematical functions, and you have lots and lots of recursion. Really cool. In a pure functional languages, you do not have side effects. This is not true anymore, but let's leave it like this. It's a subset of the larger space set of declarative languages, and these are our functional languages. As I said, I am lying because the functional languages nowadays have been enriched, always include iterative constructs. So you have iterations, even in Lisp you have iterations. There are ways to store temporary variables. So functional languages have been contaminated by the iterative word. Why? Because iterative word is very intuitive for us. So it's there are some constructs that make our life easier. And so we have iterative constructs in functional languages. At the same time, we have recursion inside the imperative languages. So now this thing is more of a blob, but the distinction is still pretty clear. Okay, now we have fun. We finish the class with some questions for you guys. This is a Pascal-like program. If you know Pascal, it's fine. If you don't know, it doesn't matter. We have to understand the concept of scope. What is a scope? I define or declare a variable, and I need to know when I can use this variable. That's what a scope is, scope of a variable. And so I will teach this by examples, or actually you guys will teach this to yourself. Question number 1. Which variables I can use are defined inside body number 1? So let's see what is body number 1. It's over here. I start with my program. As part of the program, I define a procedure, B. As part of a procedure B, I define a procedure C. The body of procedure C, it's called body number 1. So the question is, which variables I can use inside body number 1? Yes, it very much depends on the programming language. Thank you. That's why I said it's a Pascal-like program, which means that there is a static scoping, static scope. I don't even want to touch the dynamic scoping because that's, yes, go ahead. All of them. Okay, let me write them down. Unfortunately, this is wet. Okay. I'm using this one. Okay, tell me all of them. List. So wait, so we have two Ks. That's interesting. M. So are you still, what do we do about this? We what? We take the second K. Okay. Any other answer? Which variables I can use inside body number 1? Yeah?
I guess this is I, K, R from the first declaration.
So these 3.
And M.
And M, okay. Where did L go? Oh, L is there, okay. Okay, other suggestions? So your suggestion was? Other suggestions? You guys, all of you agree with either one? That's boring. Just M. Come on, you saw this a year ago. Okay, so let's go. How many of you vote for column number 1? Like almost everybody. How many of you for 2? We have a single believer. How many for number 3? Oh, we have a couple of believers. So, okay, clearly it's number 1, the winner. Not just because by popular demand, but because that's how it is. So, you define a variable, and as you go deeper in your definition tree, you can use the variables that were defined before.
But why not the 1K? I would say both, because one is inherent and one is weird.
Yes, that's a very good point. Because unfortunately, you access the variables by name. There is no other way of accessing a variable. So when a compiler or interpreter gets to a name, it doesn't know what to do, so it gets the last one. Okay? And why does it get the last one? Because this has been defined right here, so it overrides, actually right there, so it has overwritten the past one. Yes?
There won't be an error that K is already...
No, there will not be an error. You can really do this. Every time you define a new scope, so a new environment, every time you define a new environment, and within that environment you can define whatever you want. If it's been defined already, it's going to be overwritten. Yeah?
Wouldn't there be a compiler who's smart enough to divide and to differentiate between those two cases because they are different?
Again, it's not a matter of a compiler. At that point, if you can use both of them, and you write something like k equal string of k plus k, what do you know what you're doing? So a compiler, I guess in principle it could, but yeah.
I think in some use cases where you want to be like this, for example, if you have a variable x and you use it in many procedures, you name it x, and then you have your variable x outside of these procedures, and this should be, for example, a coordinate, and in these procedures you have some sub-coordinates, then you don't want that they cross each other, that it's the same x. If you want, it's a different x.
But that's the same type. You're just overwriting. Now we're talking about a character versus a real. So, okay, that was a first question. If you guys don't have clear the idea of scope, just ask. Otherwise, we move on to question number 2. Where can I use k as a real? Body 3. Wait. How can you define it in body 3? You certainly cannot use it in body 3 because it's before. In body 3, this guy has not been defined. 1 and 2, yes. Because you define it inside the procedure B, and the body of procedure B is 2, so clearly you can use there. And whatever it's inside that, so body 1. So 1 and 2, yes. Questions? No. Can the variable L, so L is there an integer, can it be referenced inside body 2? L in body 2, yes, it's its own procedure. How about body 3? No. Okay, you guys getting this? So, this you didn't have it last year. I added it today. So, what is the scope of the variable x declared as part of the procedure of the function or procedure compute? So, otherwise I'm asking where can I use x? Yes?
Yeah, everywhere besides the procedure transform. So everywhere inside of the transform.
So, in terms of bodies, you are saying
Body 1 and 3. Well, in 2 it's new thing.
okay, so for once we have different opinions. I like it. So let's take a poll. Here. Okay, so we are saying body 1, 2, 3, and main. What did you say? We.
I said body 1 and 3.
Okay. Other takes? 1, 2, 1, 2, 3. I like it. We're going for all the possible combinations. Anybody believes that it can be used in the main body? You think so? No? You think so? No. You have a question? Yeah.
Is it important that the variable x has the data type integer
Mm-hmm.
in procedure compute and then the data type real in the procedure transform? That means we have two different
Yes.
variables.
That's what we had here with the k. It was a character, and then it was a real character inside the program, and it becomes a real inside B. That's perfectly fine, as long as you enter a new environment and you can have new definitions.
But what kind of variable x do you mean?
That's exactly what I'm asking. Depending on where you are in the program, you refer to different x's. And so I'm saying that the x that was defined inside the compute. Oh, now people are changing. Say it again?
1 and 3, the first one.
Okay, so we have more believers for number 1. Yeah?
I've got a stupid question. With scope, do you mean at this point the lifetime of the variable x, or whether it can be referenced?
Where it can be referenced. Yeah, where it can be used. Okay, now that I read it again, the x is defined inside the compute. Do you guys, do you still believe in these two columns? Do you still support these answers? No. Why? Because in body number 2, x has been overwritten, replaced. So clearly these are wrong, and yes, this is the right answer. I cannot use it in the main body because I defined it inside the compute, and compute is not at the same level as main.
But I have another question. When we're thinking of time, and we think that the transform, or body 2 is assessed before body 3. So then the x is changed, and maybe the original one can just use in body 1.
You cannot do that. So you cannot switch these. They are at different level. So for body 3, the definitions are indented. So x has been defined already for body 3.
In body 2, the x is changed. So
Yes.
in body 3, I don't use my original x, which I...
So it's a new variable in body 2.
Over here, it's a new variable. You can call it xx or whatever.
But I thought that if we just have names,
Mm-hmm.
we overplace this.
Yes. So if you are in here, you can only use this one. No, I mean.
But in body 3, you can't use the original one before because
Why not? It's
it's overwritten. We have
oh, wait. It's overwritten only for the time in which you are inside this. When you get out of the transform, when you get it to the end, the old environment is restored.
And so that x has another memory location as the x before.
Yes. Other questions? All right. Then last question, and then we go home. This is tough. I don't know. Can you guys see? It was too long and I had to shorten it. The question is, which variables, what is the environment, which variables can the procedure transform access? And I guess I can do some magic. Let's see. Yes. Maybe too much magic. Okay. Here again. Woo. Yeah, I wish I could. How do I move there? Up. Okay. Do you remember the question? I don't remember the question. What is the environment for transform? Okay, what can you use inside transform? What can you use inside the transform? All right, let's write. So the answers are y. I heard y. What else did you say? Z. Y. X. That's what. X real. Okay. Other answers? Everybody agrees. So is this correct? Let me see. Transform. X real, that's true. Z, yes, that's true. Y, it's true. Yes, that's correct. See you guys on Thursday.